All right. Hello, workshop students. Let me do a couple of solutions from the quiz. Let's see, weekly quiz number 2. And I guess this is week 8, quiz 2. Maybe I'll start there. And maybe I will start with, as I said, problem number 2 here. It's a tough one. It's about this object going in a circle here. It says to make it through the loop without falling off, the frictionless roller coaster shown here must be released from rest at a height of h 20 excuse me, at a height 23.7 meters above the ground. When released from this minimum height, the roller coaster's speed at the top of the loop is. All right. So what is the speed at the top of the loop? And it gives us a little hint. The normal force, n equals to 0, when the roller coaster is at its minimum position. So, in other words, this roller coaster, in terms of energy, and so I'll draw a little picture, starts here and goes around a loop. And starting here, this is our height h. And as it comes down and it's upside down right here, it is now at a height of 2r, where r is the radius, capital R is the radius of the roller coaster loop. And so if you were just working with conservation of energy, you might start over on this side of the equation and say, okay, well, what are all the energies I could be working with? You could have a kinetic energy. You could have a potential energy due to gravity. You could have a potential energy due to a spring. You could get work that's done by a non-conservative force. That would be the heat. And so this represents everything what I'd call initial. And then final, well, we could have some final kinetic energy and some final gravitational potential energy and some final spring or elastic energy. And I like to write them all out for educational reasons and just say maybe you should start every problem involving energy like this because you have laid everything out there. Although most problems you don't need all 7 terms. For example, this one does not have a spring involved, and so this term that would have a 1/2 kx squared for the potential energy from a spring is not needed. So I'll cross that one out. There's no springs involved here. Now, there is motion involved, so kinetic energies would be involved. But if you'll notice, they said in this problem, a very important set of words here. It says released from rest. So since kinetic energy is 1/2 mv squared, the initial kinetic energy would be 0. Although by the time it gets around and upside down, it's non-zero. So we got to keep that term in, but we can eliminate this term. Now, the other one, the potential energy due to gravity, is mgh, and that one we have in both terms. We have it here from starting and here when it finishes. So, okay, I need to keep both of those around. And the work done by a non-conservative force or some kind of outside influence, we don't have that. We don't have anything influencing it from the outside, and we don't have any friction, so we can rule that out. So this is what I mean by you could write all 7 out, but the reality is you usually only have about 3 or 4 that are non-zero. And so this is the first one, mgh, and then the other 2 would be 1/2 mv squared, again, where v is when it's upside down at the top of the loop. And then the one here would be mg, and its height would be 2r. And so I'll just put a little box around here and say, okay, this is kind of the first step we would do. This would be the one related to the stuff we're doing this week on energy. But we could also go back a week, or maybe it's 2 weeks, to Newton's laws and our free body diagram. And so if we kind of draw the roller coaster, and then maybe I'll put a dotted line to kind of represent the road or a part of the road or the track of the roller coaster. You could even see it, in the free body diagram. They say, okay, so what's pushing down on the roller coaster is mg, and also the normal force. Although I could leave it off, because this question says it just barely makes it, so the normal force is 0. So at some point, I'm just going to call that 0. But maybe I'll take one step and, not call it 0, because we learned that if you add up all the forces, you can set them equal to ma. And if we make, the traditional grid here, this being the x direction and this being y direction, when it says add up all the forces, they're all in the y. There isn't any x to mess with. So that's going to make it a little bit easier. And the two of them are down, and so we have a minus mg for down, and we have a minus the normal force. So that's this part of the equation where we add up all the forces. And of course that has to equal to ma, and so I'll put an m. And so the trick to this one, the a, is to remember that it's going in a circle. And a circle, we know that the acceleration is v squared over r. And we also know the direction is always towards the center of the circle. And in my picture, since the roller coaster's at the top, the center of the circle would be down here. So the acceleration would be a negative number. Okay, let me go to another page. But what that would mean, if I take what I've just done and multiply by -1, I get all positive numbers. And so mathematically, that'll be a little bit easier to work with. And I suppose maybe now's a good time to set the normal force equal to 0, and I'll get an mg equals to mv squared over r. And I'll even get an m to cancel off. And maybe I could even then move the r over to the left-hand side, and I'll get this relationship. So this is the relationship saying its speed when it's upside down and just barely making it, because I set n equals to 0, so I'll put a little box around that. Now, the reason that's needed is because if you remember what we did earlier, maybe I'll call it equation 1 and this equation 2, I can now put equation 2 into equation 1. So let me do that right here. So this term would be the mgh equals, and 1/2 m, and then there's the v squared. So I'll put the v squared, that'd be an rg. And then this would be this other term plus mg2r. And of course, if you look at these two terms, they're identical. So you can take the 2 and the half and make 2.5. So I'll call it 2.5 mgr equals mgh. All right. I got a little sidetracked here because I might not have gone in the correct direction, because I believe they're asking for its speed. Where is it? When it is released from the site, the roller coaster speed at the top. Oh, so we want to find v. Okay. So we really want to use equation 2. But to do that, we have to get r. And that's where I'm going with this, is that if you now look at this, the m's would cancel off, and even a g would cancel off. And then to solve for r, I'll bring the 2.5 over here. And so this is saying if you take your height and divide it by 2.5, you'll get the radius of this one. Okay, so in this particular problem, it's 23.7, and if I divide it by 2.5, we're looking here at a 9.48 meters for the radius. And then if I use that up here, so there's the radius, and then times g, 9.8, that should be the velocity squared. So if I now take the square roots of the velocity, I should get v equals 9.64. Nice. And it looks like that does match what the computer here is saying is the correct answer. All right. Well, I hope that helps, and I'll try some other ones here in just a minute.